Here's a homework question from Chapter 12 in our sapling, asking us to calculate the heat energy released when 25.3 grams of liquid mercury at 25 Celsius is converted into solid mercury at its melting point. So I don't know very much about mercury, but I have some helpful tools here. I can see the heat capacity of mercury as a liquid, given to me as 28 joules per mole Kelvin. I see that the melting point is also provided as 234.32 Kelvin, and then its enthalpy of fusion, how much energy it takes to actually undergo the phase change, 2.29 kJs per mole. So that's all important information. I notice that the temperature given to me is at 25 degrees Celsius, and just make sure that your problem is something similar. It might not be the exact same numbers, but the process will be identical. And if this is in Celsius, but I know that these values, especially the melting point, is in Kelvin, I am going to just simply quickly convert that from Celsius to Kelvin so we can generate common units. So it is at 298 Kelvin units, adding 273 to the Celsius temperature. So the initial temperature of our mercury is 298 Kelvin units. The other interesting point on the curve comes from the freezing point or melting point, which is given to us as 234.32 Kelvin units. So if we're starting at we're at a liquid phase, and I know it will cool, so there's our first line segment, and then it will undergo the phase change. There's the second line segment. So line segment A to B is an MC delta T problem. We have a temperature change. And line segment from B to C is what we call as the enthalpy of fusion, where we actually undergo a phase change. So two line segments. Alrighty. Other preliminary work, I noticed that they're giving me a mass for my liquid mercury, and yet these values are given to me in a mole. So we have a little bit of mole map work to do. We have 25.3 grams is the value given for me in my problem. Make sure you're using your own. And I'm going to do just a simple mole conversion by using the molar mass of mercury, which, I don't have a table in front of me. I'm doing this from memory, but I believe it's 200.8 grams per mole. You might want to double check that. It's 200.6 or 200.8. Maybe I should Google. What do you think? You may fast forward. I'm going to Google molar mass of mercury. And 200.59. See, I'm glad I did that then. We'll just repair that. 200.59, it was 200.6. I'm going to round that. 200.6 molar mass of mercury. That's what I'd get for not memorizing the periodic table. So I have 25.3 grams provided for me, and I'm going to divide by that molar mass I just looked up, 200.6 grams per mole, the molar mass off the periodic table, and that I'm finding is 0.13 or 0.126 if I carry more sig figs, and there's the number of moles then. Alrighty, so let's consider line segment AB, where I have liquid mercury at 298 Kelvin, and it's going to cool to the point of where we'll see the phase change begin. The number of moles we just calculated, 0.126 moles of mercury. And again, I'm using that so that I have like units when I grab the heat capacity of liquid mercury. That's given to me as 28.0 joules per mole Kelvin. Notice what's happened is now we're able to actually cancel the mole unit. And in our next step, we have to cancel out that Kelvin, so we need a delta T. Temperature started at 298 Kelvin units and is cooling to the phase change of 234.32 Kelvin units. And that looks like a delta T of 63.68 units. So let's solve for 0.126 times 28 times 63.68 Kelvin unit change there. And the joules is coming out as 224.66 joules. So there's the answer to the first line segment. We had a second line segment where we have to undergo the phase change using the enthalpy of fusion value. So again, I'm using the number of moles we calculated from above, the number of moles we solve for using the correct molar mass, and I'm simply going to use this conversion that it takes 2.29 kJs for every 1 mole to undergo the phase change. And let's see, looks like the answer wants to be a kJ, so I'm going to keep this as a kJ. And then I also need to back up here and make sure I end with like units. I'm going to divide by 1,000 to get a kilojoule so we can add like units, and the target there was a kJ. So sliding that over 3 spots, it gets to be 0.22466 kJs. Let me actually calculate 0.126 times 2.29. 0.126 times 2.29. Yep, I just checked my calculator. That's giving me 0.28854. Of course, we know that we need to sum that total to find the total amount of kJs there. So 0.28854 is still on my screen, so plus 0.22466. And that value is 0.5132. How many sig figs should we type in? It looks like the least amount here is 4, here's 3, so we better go to 3 sig figs, 0.513. And that will help you with this problem.